All right, wrapping up DeWitt's long chapter on interpretations of quantum theory. So we're still on standard interpretations, though we've started contrasting them with their competitors like Einstein's more commonsensical but certainly false hidden variables view. Why is Einstein's view false? Wait till chapter 28, we'll talk about that. So when I say here variations on this view here means standard or Copenhagen or collapse interpretations. Those are ways of saying the same thing. And we're going to bring out that there isn't a standard reading of standard interpretations. There isn't a standard Copenhagen or collapse interpretations. Here we're going to get three flavors or varieties of Copenhagen or standard interpretations. Perhaps the most common one DeWitt calls mild measurement dependence. So we take a narrow view of what counts as quantum phenomena. It's only small things moving fast. That's a little awkward because everything seems to be made up of that stuff. But nevertheless, it's defensible to say quantum theory only applies to little stuff moving fast. You combine that with a broad view of measurement. So again, we have no good theory of what makes something a measurement operation. But we can commit ourselves to a pretty broad view of measurement so that the wave function will collapse relatively early. So the first detector performs a measurement, collapses the wave function, and so this view is relatively tame as standard interpretations go. It does a nice job of confining quantum craziness to the micro level. Schrodinger's cat was never in a superposition of alive and dead states because wave functions will always collapse because of this broad view of measurement we're taking before they, as it were, bleed up to the macro level. So the fundamental components out of which everything is made seem to play by these bizarre quantum rules, but you can try to find ways to contain that bizarreness to the micro level. Next view, moving up, would be moderate measurement dependence. Like the predecessor, this takes a unlike the predecessor, it takes a broad view of quantum phenomena. Everything is in principle a quantum phenomenon. So you or I or a cat could, in principle, be in a superposition of, say, live and dead states, but like the narrow or mild measurement dependence, it takes a broad view of measurement. So as a matter of fact, superpositions, wave functions, are always collapsed before they can bring their craziness up to the macro level. So there's nothing other than the fact that lots of measurement operations are going on that prevents Schrodinger's cat from existing in the same kind of superposition of states that an electron could exist in, but it pretty much never happens. Radical measurement dependence takes a broad view of quantum phenomena, so you and I and cats and tables are in principle quantum phenomena. A narrow view of measurement is tied only to consciousness or perhaps to human consciousness. So wave functions are not collapsed until a conscious being takes a measurement. This requires putting a lot of weight on the distinction between the activities of conscious beings and other things. It's a pretty weird view, but so is every view in this neighborhood. So the world, when unobserved by conscious beings, is full of superpositions at the macro level. It's only when conscious beings perform observations that the wave functions collapse. So these are all ways of developing a kind of standard or Copenhagen view. But keep in mind that the heart of the Copenhagen view resists a lot of these developments. Bohr wants to say, I just don't think these questions have answers. I think we should stop asking them. So these are ways of giving more of a physical interpretation to a standard or Copenhagen view than some proponents of standard or Copenhagen views want to give them. Next, we have hidden variable views, which, as we've seen, insist that the standard view is incomplete. So Einstein says particles have classical properties. They have a speed, a spin, momentum, all of that. It just is our size and their size and physical facts about our ability to interact with them that prevent us from ever knowing these things. So Einstein's strong measurement dependence of space and time in special relativity gives way to his realist inclinations here. The math does not present particles as having determinate locations or spins, etc., but they must, because that's how reality works, Einstein says, so there's something missing from the math. This is the most appealing view. It makes the most intuitive sense to us. It turns out, for reasons that we'll see in the next chapter, it can't be right. Now, let's note that we've only got a difference of one letter between the name of David Bohm, who is a realist, a hidden variable view proponent, and the name of Niels Bohr, B-O-H-R, who is the architect of standard or Copenhagen views. I am not requiring you to keep track of these people's names, except I might need them to ask questions, and since it's an open book test, you should be able to figure that stuff out. But don't misuse the names. Don't say Bohm when you mean Bohr. Try to avoid the names if you're not comfortable with them. Bohm's view is a very intuitively attractive view. It makes Einstein's realism compatible with the mathematics. It's a way of developing the math for the theory such that particles have a determinate position. Unfortunately, you need to posit a thing called a guidance wave. This is in many ways somewhat similar to Heisenberg's system mathematics for quantum theory. You can talk about a particle-ish picture, but for Heisenberg, the system math won't reduce to any determinate location for particles. In Bohm's view, it will. So you can put everything intuitively in a place. Everything has the classical properties. Unfortunately, the guidance wave looks like it transmits influences at faster than light speed in order to make the math work out. So that was a reason for rejecting it. When we look at chapter 28, we'll see that nowadays everybody seems to be stuck with some kind of faster than light speed influence or communication or something. So this is less of an objection to Bohm's view than it had been. Nevertheless, DeWitt does a nice job of explaining why this is still a minority view. Bohm's problems with relativity would take a lot of time to lay out. Let's just note that many physicists think Bohm's view fits less well with general relativity than standard Copenhagen views or other non-collapse views like many worlds interpretations that we'll get to in a minute. So it's kind of ironic that Bohm is the person whose view is closest to Einstein's, but has arguably the biggest problems fitting in with Einstein's theory of relativity. Bohm's math is designed to be equivalent to the standard math, and because of that, it can't be any better. So relatively few physicists have wanted to drop the math they're used to for the sake of a view that just sort of feels more comfortable. And finally, I don't know why DeWitt didn't mention this, if you want to develop a physical interpretation here, you're going to have to confront sort of what a guidance wave is exactly. And so it can feel like a lot of the craziness that infects other interpretations of quantum mechanics gets smuggled under the rug in the notion of a guidance wave. So Bohm's view is an appealing alternative out there. It's got problems, so does every view. The last family of views are many worlds interpretations. These are non-collapse interpretations, as are hidden variable views. There is no collapse of the wave function for realist interpretations, also called hidden variable views, or many worlds interpretations. So the superpositions persist. Where does the wave energy go? It doesn't go anywhere. It's just a different possible world, a different version of the universe. There are different ways of trying to characterize this. So the idea is every time a measurement operation is performed, the universe splits. And so if we find a dead cat, our counterparts find a live cat, and they inhabit a world or universe different from ours, starting at the moment there is a measurement operation. This view gets taken quite seriously by scientists, largely because it takes the math at face value. It is the most direct interpretation of the mathematics, but it posits this crazy multiplicity of worlds that we are in no position to detect, right? We're stuck in our world, and there are these other possible worlds going on without us. And so the world is just constantly splitting and splitting and splitting. So it's not a very empiricist view because it violates Occam's razor. Do not multiply entities without necessity. This says universes are sort of cheap. They arise all the time. So I'll do this part in a minute here. Let me situate the big picture. After you read the chapter again, and maybe you listen to this lecture again, you should, keeping in mind that it's an open book exam, be in a position to articulate the strengths and weaknesses of standard interpretations, hidden variable or realist interpretations, and many worlds interpretations. That's a realistic goal for your time spent on this chapter. This stuff is not easy, but you've got some time. You can listen to this as many times as you need to. You can contact me for help. Finally, this in many ways is an unprecedented development in the history of physics, just like the step back from universality is. Generally, we had a physical system and we had to construct math in order to describe it quantitatively. Newton has to invent calculus in order to get his physics to work. Here, physicists built a successful math and are still struggling to give it a physical interpretation, rather than having a reasonably well understood physical setup that you then try to interpret mathematically. We've got a mathematical interpretation that we struggled to interpret physically. These are strange times we're living in. This stuff, I think, repays reflection. It's maddening, but it's fascinating. Please think about it and hit me with any questions you've got. Thanks as always for your time and attention.